You type a question into a prompt box, hit enter, and seconds later, a highly intelligent response appears on your screen. The interaction feels frictionless, almost like the machine is thinking in real time. But that response is the final output of a massive, multi-stage manufacturing lifecycle. The intelligence we see is a product that was built long before the question was ever typed. Historically, AI development was trapped behind a physical bottleneck. Older systems, like recurrent neural networks, process data tokens one by one. They had to finish calculating a single word before they could even look at the next, creating a hard limit on how fast they could learn. Reaching the scale of modern generative AI required tearing down those traditional computing pipelines. Engineers had to build a system where every piece of hardware and software was designed specifically for massive parallel processing. Google addressed the hardware side with the Tensor Processing Unit, or TPU. With a standard processor, the TPU uses a systolic array to keep data moving. It works by pumping data through thousands of logic units simultaneously, completing matrix multiplications without stopping to access external memory. The software side required an equally massive shift, the transformer architecture. It replaced sequential reading with a system that ingests entire data blocks at once. This is powered by multi-headed attention, which mathematically maps relationships between every word simultaneously, rather than in order. These upgrades provided the high-throughput parallelization needed to support modern models. Engineers had finally built a high-speed digital brain, but at this stage, the network is still a blank slate. To give the empty model a baseline understanding of the world, it undergoes pre-training. It is fed trillions of words from across the internet, learning to predict the next word in a sentence over and over until it recognizes the patterns of human language. This is called in-weight learning. As the model processes this massive dataset, factual information and grammatical rules are encoded directly into the physical parameters, or weights, of the neural network. This phase is governed by mathematical scaling laws. Early models followed the Kaplan law, prioritizing making the model as large as possible. But newer research, the chinchilla scaling law, proved performance is maximized only when model size and training data volume are scaled equally. By the end of pre-training, you have a highly capable base model that understands the world. However, it is still too unpredictable and unfiltered to be used as a safe assistant. The next step is alignment, essentially an etiquette school where the model is taught to follow human intent and provide helpful, safe responses. The traditional method, RLHF, uses a separate reward model to grade the AI's behavior. The AI generates a response, the reward model scores it based on human preferences, and that feedback is used to slowly adjust the AI's policy. A more efficient approach is direct preference optimization, or DPO. This eliminates the reward model entirely. DPO forces the model to choose between a preferred human answer and a rejected one, adjusting logits directly for faster, more stable alignment. With these behavioral safeguards in place, the model is ready to deploy its most powerful emergent trait, in-context learning. Using internal circuits called induction heads, the AI can now match and copy patterns from your specific prompt to solve new tasks instantly. The AI is now polite, responsive, and highly adaptable. It's ready to be released to the public. In the real world, this system works as intended. You can have a nuanced, sophisticated conversation that spans dozens of messages within a single window, but there is a flaw in the architecture. The moment you close that chat session, the AI suffers from total amnesia. When you start a new conversation, it has no memory of who you are. Permanent in-place learning cannot fix this. It is computationally too expensive to retrain a massive model on every single user's daily data. And in-context learning is only temporary. The patterns matched by those induction heads only exist as long as the prompt is active. Once the session ends, that information is gone. This creates a mathematical tension. We have built an advanced conversational brain, but by design, it cannot remember you from yesterday. The solution is the integration of persistent memory layers. This acts as an external storage system that sits alongside the model. Persistent memory allows the AI to store your preferences and past interactions in a secure database. This lets the model recall relevant information across different sessions without needing a full, expensive retraining of its weights. Modern artificial intelligence is a coordinated stack of silicon hardware, transformer layers, and memory. It is a highly engineered system that follows predictable rules. Understanding this pipeline reveals the assembly line of human knowledge that actually generates the response. It isn't magic. It is an integrated manufacturing process designed to capture and recall the world's information.